Good afternoon. Do you have any questions? None? Okay. Last time we looked at static factors of safety for a bolted joint. I guess set screws work the same way, except that your KM has to be a little bit different. It's not the whole thickness of the part, but only counted partially, as we talked about it before. Today, we're going to take a look at the torque requirement for the preload. Remember that if you need a particular preload in a bolt, you don't actually apply an axial load to the bolt. What you do apply is a torque. And by tightening the nut, you create the preload in the bolt. The preload can be measured if you really want to do it. In other words, you can install strain gauges on the bolt and measure the strain in the bolt and therefore find the stress, if that's what you really want to do. And in experiments, we actually do that. But in order to affect a particular preload in a bolt, what we measure is the applied torque. How much torque is required in order to tighten the joint, produce a preload. So we would like to take a look at a relationship between the torque and the preload. In other words, how do we relate the two? 01, let's see. This is a distribution of preload. This is table 813. A distribution of preload for 20 tests of unlubricated bolts, torque to 90 Newton meters. This is same materials, many different experiments, and you do get these numbers. So when you torque it up to 90 Newton meters, you get all of these numbers depending on the particular test that you're running. But remember that they're all made on the same material, same thickness, everything is exactly the same. So these numbers vary somewhere between about 23 to 42. With an average of, as you read below the table, 34.3 kilonewtons and a standard deviation of 4.91 kilonewtons. Do you all know what standard deviation is and what it means? Yes? I need not go through it? Okay, good, thank you. So when we take an average like this, we can sort of relate this load to the applied torque. So on the average, this is about the load that you require, the load that you produce, Fi. It's about a third of 90, approximately. A third of 90 is 30, this is 34. So there is that relationship that we can come up with. This is for a particular torque. We can write the actual relationship between the preload and the applied torque by looking at the equations for the Acme thread. Remember when we were looking at power screws on Acme thread, there was a relationship between the torque that was generated by the Acme thread and the load to be raised, we called it. We said TR, torque to raise the load. This is essentially the same thing, and a threaded fastener essentially looks like an Acme thread. So we can use, except for the angle, of course. The angles are different. This angle is different. So we can use Acme thread equations in this case. In fact, we've used it. We used it in the example problem of the C-clamp that I did last time. We used basically this very same equation. So let's take a look at the equation for Acme threads in power screws, that is. And we did that, and this is that equation. Fi dm over 2, Fi is essentially our preload, times L plus pi f d sub m secant of alpha, that angle is 2 alpha, divided by pi dm minus f L secant of alpha. F is the coefficient of friction for the threads. Alpha is the angle. That is how much torque you need in order to overcome the friction in the threads and produce this preload. Aside from this torque, and if you have a collar, you remember we talked about collar friction as well. Here we don't have, you usually don't have a collar, but we have a washer. And that washer acts in exactly the same manner as the collar does in power screws. So we have to add the torque to that. And that, again, from what we had before, Fi, coefficient of friction of the collar now, times dc over 2, where dc is the mean collar diameter in the equations for Acme threads. In our case, if this is the bolt, D, and that's the washer diameter usually is approximately 1.5 D. And for this, we use the mean washer diameter. That's what DC is. That. So DC is equal to 1.5 plus D over 2, 1.25D. Also, if we use a coefficient of friction, actually, well, I'll talk about that a little bit later. But that's mean collar diameter. And we also had this equation. Tan lambda was equal to L over pi dm. Remember, this came from taking a thread, 360 degrees, single-threaded screw, L and pi dm, with that angle equal to lambda. If we substitute all of these into this equation, this is what we get. We get T equals dm over 2d times tan lambda plus f secant of alpha. Remember, lambda is the thread angle. 1 minus f tan lambda secant alpha. Plus, we get what we get from the collar friction, which comes out to be 0.625 F sub C, all times FID. And if you look at the equations for the Acme thread, this D doesn't exist really. We've written in everything in terms of Fi with no E. This D is here to just simply cancel out that one, so that that equation becomes the same as this equation. We just put a D here and a D at the end, and they just simply cancel one another out. Now, if we assume that the coefficient of friction, both for the collar and the washer, is 0.15, then we find that this bracket, this whole bracket, which we call K, comes out to be approximately equal to 0.2 if we incorporate everything there. Remember, alpha in this case is the angle between two threads, and lambda is the thread angle as it creates the helix. So, as an approximation to the torque, we say take T approximately 0.2, write it generally and then we'll say 0.2. T is equal to K Fi D, and with K approximately equal to 0.2, then T is approximately equal to 0.2 FID. So if you're asked to estimate the tightening torque for a preload of 10 kips, that's the equation you use. You have the diameter, whatever bolt it is you're using. Fi should be 10 kips, and you find very easily the applied torque. Now, if we look at this distribution of preload Fi untested lubricated, these are lubricated joints, and notice that these are much closer to one another. The standard deviation is much lower. Use this approximate equation unless you have something specific like what you see on the screen. For those types of materials in contact or in the grip, those are the values. And notice that a middle value for all of what you see on the board is approximately 0.2. Go from 0.09 to 0.3 with an approximate value of 0.2 for the middle. That's what we're going to use to estimate the tightening torque. If you need exact values, then you have to come up with the exact value of the coefficient of friction and use that equation to find that value. But most of the time it's not necessary, because remember that all of these are approximate values. What we have taken, for example, for the way a load distributes from underside of the bolt head to the top of the nut is like that. We said this angle is, we assume to be 30 degrees, which is actually a good approximation, but it is an approximation. They have it for 30 degrees, they have it for 45 degrees. If you refer to this picture in the book, this one. For example, notice here, Michigan 30, that's the one we're talking about. Then you have a 45 as well, and you have others that have come up with these various values. The best approximation is that of the FEA, and that matches the Michigan 30 value at about 0.4 D over L. So that's the applied torque. That's how we find how much torque is required to give you the preload that you want. Any questions? Let me show you this too. I might have shown you this before, I don't remember. But this is a good graph, although it has no values on the x or y axis. But good stress strain diagram showing you qualitatively the relative values of the tensile strength, yield strength, and proof strength of the bolt. So tensile strength at the end, yield strength in the middle, and proof strength over here. So that's a good one to refer to most of the time. Now, leave that there. One more thing before we take a look at the fatigue of bolts. Fully gasketed joints. In many instances, rather than using a confined gasket, such as an O-ring or a confined gasket in a hole, we use full gaskets. For example, if you have ever looked at the cylinder head in a car taken off, the cylinder is connected to the cylinder head with bolts, and there's actually a full gasket that goes all around and separates these two. So that a fully gasketed joint will essentially look like this. Assuming, for example, for a pressure vessel or whatever else there may be. This is the head. Over. Oh, don't want that there. That. Cylinder head, body of the cylinder, a full gasket. Gasket that covers everything between the head and the body of the cylinder. Now, you recall that when we wanted to find the stiffness of the member, we said we'll make the assumption that the load is distributed like this, with however many members we may have. So this would be, in our case, would be member 1, then we have 2 member 2s, which if this is symmetric, they'd be the same, and this member 3. For each of them, we find a value of k, then we combine them. Each of these values for k's are found using this equation. And then we say k, the spring constant, is F over delta is equal to AE over L. Now, when we want to combine these, let's call it A sub I. Yeah, A's are different. Could be different. Like that. The load is the same for all, right? The same load, same compressive load is applied to all of the members. Then we say 1 over k member is equal to the summation of 1 over ki, or 1 over k1 plus 1 over k2, and so on and so forth. Now, if we have a fully gasketed joint, such as this, then the modulus of elasticity of the gasket is much, much smaller than any of the members, even if the gasket is a soft metal, such as copper, for example. The modulus of elasticity is much, much smaller than that of the member. So, looking at this general equation, if I look at the whole joint here and say, okay, I compress this joint, I find delta, then I have a force F with which I've compressed this. But looking at the delta, at the deformation, compressive deformation of the joint, what is the relationship between the compression of the member and compression of the gasket?
The gasket is much smaller.
Compression of the gasket is smaller than that of the member? What about E for the gasket? Larger or smaller? Okay. Okay. The K is smaller. Yes, yes, that's correct. That's correct. The K is smaller. That's true. That's true. But we don't use K. What do we use? 1 over K. So 1 over K gets large. So if you just simply take a look at the deflection, when we compress this joint, we can say with pretty good approximation that all of the compression is going to occur here. Let's say the gasket is made of some polymer material, rubber, for example. So only the rubber will deform. The other two almost don't deform at all. Now, if you want to apply this and go through this process, that's fine. You'll get the answer. No big deal. But there's no sense in doing that. So when we have a fully gasketed joint, we say since this deflection comes almost entirely from the gasket, that's the only thing we consider. We say F over delta, which is K, is the stiffness of the joint. So in this case, K gasket is the same as K of the joint. Everybody okay with this? And rather than going through this process, since the gasket is usually pretty thin, what we say is that we'll just take a look at the gasket as though it were an axially loaded member, which essentially it is. So if I'm looking at a fully gasketed joint, and this is a pressure vessel that's connected via, let's say, 5 bolts, then that's what the top of the pressure vessel looks like, the head. And that's exactly what the gasket looks like, except that, sorry, they're not there. Here, we have no area. So gasket area is this. Everybody okay with this? We have a round gasket, have a few holes in it where the bolts will pass, and that's the area of the gasket. Now, the area of these bolts relative to the area of the gasket is usually small. So they can be neglected if that is the case. If they are large, you have to take them into account. But if they're small, you can neglect them. So we say, therefore, K of the member, and we are now looking at this equation, is AG EG over LG, where LG is this distance. LG is the thickness of the gasket. This is the same PL over AE equation. So that's the stiffness of the member, which is the same as the stiffness of the gasket. Any questions? Oh, I guess if I said this is a pressure vessel, so I better take the area in the middle off, huh? That's more like that. That's the pressure vessel. When we have a fully gasketed joint, the joint will be sealed if the gasket is under a specific pressure. And that pressure is generally provided by the manufacturer. For example, it says this gasket can take a pressure up to whatever, provided you have a pressure on the gasket. So there's one pressure here inside the cylinder, one pressure you put on the gasket. These are different from one another. It says if you put such and such a pressure on the gasket, it'll take up to 1,000 psi, and it'll still be sealed. That pressure that you put on the gasket must be uniform. In other words, the same pressure that you have here must have here, must have here, must have here. Otherwise, your joint is going to be out of balance. That pressure can be defined as the force in the member divided by the area of the member. What do we call member? The gasket, for this purpose. So the force on the gasket divided by the area of the gasket is equal to the pressure on the gasket. Does everybody understand that? So that's how we affect the gasket pressure. So we define that gasket pressure as negative, because it's a negative force. Oh, not Km, Fm, sorry. Force in the member divided by the area of the gasket per bolt. So, and this one should be all of these. I'll come back to that. Area of gasket per bolt. That's why we divide that by N. The same thing is true here. The same thing is true here. We found Km by looking at only one bolt. So if you have a number of bolts here, your Km should be calculated for this area. However much of that area belongs to this bolt. AM is calculated on that basis. Sorry, Km, AM, both are calculated on that basis. And you divide them up exactly like this, and the bolt spacing should be the same for uniform pressure. Everybody understand that? So this is km per bolt. Maybe I'll write that here. Ag per bolt. And so maybe I'll change this one to Ag capital. Total area of the gasket. That little Ag, A of the gasket per bolt. So that if I write that for clarity, Ag is equal to Ag divided by the number of bolts. So here we have 5 bolts. We calculate this area divided by 5, and that's the area that we use for each bolt. The member stiffness is calculated on that basis as well. Any questions? Now, in order for the joint to stay intact and not leak, we need to have some sort of a factor of safety on the load in the member. Remember that we said in order for all of these equations that we talked about to be correct, the pressure on the member or the force on the member must be negative. Remember, this is a negative pressure. This is a compression. Should never become equal to 0. Recall that that force was Fm equals 1 minus C times P minus Fi. So this must always be less than 0. You must always have a little bit of preload under all circumstances. That's for joints that are not fully gasketed. For joints that are fully gasketed, once again, this is limited. Not to 0 this time, but to whatever is required to give it this pressure. So we put in a factor of safety N in this case. And we say, okay, this is Fm. We now substitute this Fm over here, and we get this equation. Pressure is equal to N over Ag times Fi minus Np times 1 minus C. That's the pressure on the gasket. N number of bolts, Ag total area of the gasket, Fi the preload, P the externally applied load, G the load, the joint constant, N factor of safety. Whatever factor of safety you need, you put in the pressure, you put in your factor of safety, you find out how much Fi you need to make sure that this doesn't happen. With the applied external load, of course. So, the pressure must be uniform. If the bolts are too far apart from one another, then we have good pressure here where this bolt is, good pressure where that bolt is, and if there's no bolt here, there'll not be enough pressure there. So bolts must be close enough to one another to make sure that you get a uniform pressure. On the other hand, they must be far apart from each other, so that you can get a wrench in there and tighten them. If they're too close to one another, then they interfere with that. So there's a minimum and a maximum for what we call bolt spacing. And we base that on what is called bolt circle diameter. dB. We say the distance between two bolts, two adjacent bolts, must be no less than 3 bolt diameters and no more than 6 bolt diameters. So this bolt spacing, this distance between the bolts, call it D, must be less than, don't call it D, because D is bolt diameter, call it A, less than 6D, greater than 3D. And to put that into an equation, so okay, we find the circumference of the bolt circle, pi dB, divide that by the total number of bolts, we get the bolt spacing. Take the circumference, divide it by the number of bolts, you get the distance between two bolts. This must be less than or equal to 6D, greater than or equal to 3D. As a general rule, must be less than 6D to make sure the pressure is uniform, must be greater than 3D so you can get a wrench in there. Any questions? Okay. More often than not, and except for bolted connections in structures where they rarely see considerable fatigue loading, in many instances we do get fatigue and of bolted connections. And therefore we must not only to make sure that statically the joint is safe, but that also it has a desired life. So we have to take a look at fatigue. For that, I refer you to this page in your handout. The same argument is also in your book. Your book used to treat this section in a special case where the external load varied between 0 and a maximum only. So that's why I put that sheet in the handout. But now the book actually covers this in a general fashion, meaning that the force does not go from 0 to P, but from P1 to P2, and then adopts it to the more specific type 0 to P. So here, the analysis goes exactly the same as the analysis that we've had up to now. In that, assuming all of these are known, and that would be the case, these are material properties. I'll talk about SE in just a second. SUT, SY, Pmax, Pmin. Fi is the preload and At is the tensile stress area. Once you have a connection and you know your bolt material, all of those can be found, except for SE that we haven't talked about. So this is for bolts, endurance limit for bolts. Now, you can use the equations that we had, find the tensile strength, 0.5 SE, take 0.5 times that to get SE prime, apply correction factors, so on and so forth, and that's fine. But in general, since bolts when manufactured have specific conditions, in other words, surface conditions, whether they're rolled or cut. And in most fatigue applications, by the way, we use rolled thread, not cut threads, because they have less stress concentration. But in many instances, this value will be given. The only thing that we need to worry about in general are these. This is the bolt. We need to worry about stress concentration here, right under the bolt head, and right here at the start of the nut. Those are the two locations of stress concentration. So we can go through that process, come up with these values. And then if we go to table 816, you see stress concentration factors for threaded elements, both cut thread and rolled threads, both for the fillet at the very end and for the threads here. In other words, for the threads would be here, for the fillet would be there. Those are stress concentration factors. And you can apply those and get the value of SE. Or we can use fully corrected endurance strength for bolts. Endurance limit, endurance strength, same thing. For bolts and screws with rolled threads. In most cases, we do use rolled threads. So these are fully corrected. In other words, Ka, Kb, Kc, whatever, plus the stress concentration factors. They're all in there. And in this case, since we only have axial loading, we've reduced the strength by the stress concentration factor. In most of the problems that you solve, you can just go in here, figure out what class of bolts you have, what size range you have, and that'll tell you what the endurance limit is. And simply use that value. So when I say, given a joint, you have all of those values, I mean, you have SE, SUT, whatnot. That's these, the ones you see on the very top. So that's how you find this SE. The rest of those, of course, you can get from the tables for various grades of bolts. Tensile strength, yield strength, proof strength, whatnot. The load varies between a maximum value and a minimum value. And we need to find the mean and alternating values of the stress in the bolt. By definition of alternating load, it's F max minus F min divided by 2, which is equal to C times P max minus P min divided by 2. Let's see, it's not there. Okay. So we have FA is equal to F max minus F min divided by 2. F max is C P max plus Fi. Not all of the externally applied load goes into the bolt. Only a fraction of it goes into the bolt. That fraction is called the joint constant, C. So the load in the bolt is C times P max, P is the externally applied load, plus Fi, minus C P min plus Fi divided by 2. And of course, this is equal to C times P max minus P min over 2. The Fi cancels out. meaning that the only part of the load that is fluctuating is C times P, not Fi. Fi is always there. Any questions? Similar to this, Fm, mean value of the load, F max plus F min over 2. These are the original equations that we had. And here you substitute, and you get C times P max plus P min over 2 plus Fi. This time it doesn't cancel out because you're adding the 2. You get 2 Fi divided by 2, or Fi. In other words, that equation. That's where these equations come from. And in here, say F max is this and F min is that. You substitute, you find that. The alternating stress is Fa divided by At. Here's Fa. We divide it by At, and this is what we get. Mean stress is Fm divided by At. There's Fm. We divide that by At, and this is what we get. Now, drawing these on a sigma A, sigma M, or Goodman line failure criterion loci, because now that we have sigma A and sigma M, all we need to do is define our strength criteria, Goodman, Soderberg, Gerber, what have you. Draw that, draw the load line, and find the cross section and come up with the factors of safety. So here's the Goodman line. Remember SE, we find from that table if at all possible. Otherwise, we use the usual procedure with the stress concentration factor. Now we come to the value or the drawing of the load line. Let us first assume that there is no external load. If there is no external load, of course there's no variation in the load either. In other words, P max is equal to P min is equal to 0. No external load. There's no variation of the load either. And if I want to plot that point, where would it plot? What would I have actually? If the external load is 0, what do I have?
Sigma M equals the preload.
Not quite. You would be right last week, but not this week. Because remember that we have actually applied a preload to the bolt, which has created a tensile stress in the bolt, hasn't it? This is your static load. Remember we talked about a number of things. We talked about alternating stress, mean stress, stress range, maximum stress, minimum stress, also static stress, that I said is somewhere between the maximum and the minimum. It is not equal to the mean necessarily. And I gave you as an example the weight of a beam, for example, which is under bending, as a static stress. Here we have torqued the bolt to its preload, generated a stress which is going to be there whether or not we apply any external load. Does that make sense? So it's not the mean stress anymore. It is the static stress, sigma S. But we plot it on the mean axis because it's not alternating. So when you apply your alternating stress, you're going to apply it on top of this preload stress, correct? So we start from here. Whether I apply any alternating stress or not, that's going to be there, like it or not. And then I will plot my point. Well, my point is plotted here, let's say. That's sigma m. That's sigma a. And that is my load line. And that's the Goodman line. The procedure is exactly the same as before, except that now the equation of the load line is a little bit different. It does not pass through the origin. So we write an equation for this line. The slope of this line, take a look and see, is equal to that distance, which is sigma a, divided by that distance, which is sigma m minus Fi over At. Agreed? So the slope of this line, sigma a, that. If there's anything you don't understand, please tell me. So now we can write the equation of that line. Let's see, how have we written the equation here in terms of sigma m, okay? So we can write the equation of this line. You can write it any way you like. Sigma a in terms of sigma m in terms of sigma a. What's on the screen there actually written in terms of the coordinates of intersection, but is sigma a in terms of sigma. So sigma m is equal to, first, Fi over At, and then it increases by the value of sigma a times the inverse of this slope. So Fi over At plus sigma a divided by the inverse of that slope. Did I do that right? No, it's written differently. Let's see. Sigma m is equal to that slope of the line, Fi over At times. I have to write it in terms of. The coordinates of the point. Let me show you what that is. That's this point. Otherwise, I'm going to have 2 sigma a in there and 2 sigma m's, and it's not going to make sense. Let's write the equations in terms of that. SA and SM. So SM is equal to Fi over At plus the inverse of the slope multiplied by SA. This is like saying this. You can write the equation of this line as y equals b plus mx. Right? Now we've switched it. X equals y minus b divided by m, or y over m minus b over m, basically that equation. And we've used this point rather than the point here, we've used that point in our equation. You can check it This is a straight line. We can check it. We know the coordinates of 2 points, this point and that point. Say if SA equals 0, what is SM? SA equal to 0, SM equals Fi over AT, which is right. And in here, we say, what if SM equals Fi over AT? SM equals Fi over AT. These two cancel out, and SA should become equal to 0 because sigma m minus Fi over AT is equal to 0. If you have this point. So that's the equation of this line. One important point to keep in mind here is to make sure that when you want to calculate the factor of safety, you write it like this. You write the factor of safety for fatigue equal to SA over sigma A, not SM over sigma M. Because you're looking to do a fatigue analysis that should only include the alternating value of the stress. The mean value of the stress always includes this. That's not a part of your factor of safety. Factor of safety is the factor by which you can multiply the externally applied load, not the existing one, the externally applied load before it gets to some threshold. So this factor of safety has to be calculated that way and not this way. And obviously you see the difference. One of them is this ratio, that divided by that. The other one is that divided by this. Two different animals. Not the same at all. The numbers will be very much different from one another. So that's how we calculate the factor of safety in the case where we have a preload on the boat. Any questions? Let's see, yeah, let's go through this example and finish it, and then we'll take a break. This is the continuation of the example that I did for you last time. Do you have any questions before I do that? Okay. Continuation of the example that I did for you last time. It says in problem 834 of the book, assume the pressure, let's do this one first. It's the easier of the two. Let's do this one. We did part of this problem. Last week, we did part of this problem on Thursday. We did the static part.
For the end proof, how come you used FB instead of FI?
End proof SPAT minus FI divided by CP. How come I use what?
You use 9.65 instead of 9.05 for the FI? Isn't FI 9?
Yeah, you're right. No, you're right. You're right. Should be 9.05. I wonder if I've calculated it that way or not. No, it should be 9.05. You're absolutely right. Run my calculations, see if I've actually done that or just miswrote it and not take it into consideration. But that's what we did last time. Yeah, I'm using 9.65. Whether or not I've done that, I don't know in the calculations. Is it, anybody has a calculator? Run that number, see if you get 4.03 or not. But that's, we can correct that if that's the case. But we're going to do this on fatigue right now. Assume the pressure inside the cylinder changes from 0 to P. This is the more, the easier of the two situations, which results in an external load of 2 kips per bolt. If the bolts are SAE grade 5 and are preloaded to 75% of their proof strength, check all relevant factors of safety and load factors. So we did that statically for last time, factors of safety static, in proof, and for joint separation. We're going to do the fatigue part now. And notice that it says it varies between 0 to P, and this is very common. For example, the gas cylinders that you use with your barbecue, you keep pressurizing them and depressurizing them. When you depressurize them, essentially the load is 0. If that were a pressure vessel, this is what would happen to its bolts. So we do fatigue here on this one. Sigma A, CP over 2AT. We had that in both cases. Actually, let me show you where that comes from. It comes from here with P min equal to 0. So you get C P max over 2. And rather than just calling it P max, because that's the only P we have, we just call it P. So we have CP over 2AT equals sigma A, where P is the maximum value of the force on the bolt. Everybody understand that? That's where that comes from. Sigma M is sigma A plus Fi over AT. The reason why that happens is that if the force varies between 0 to some value, take a look in here. Actually, yeah, these two equations. If P min is equal to 0, this is Cp max over 2, this is Cp max over 2. They're exactly the same. In other words, I can write in that case, in our case here, that Fm is equal to Fa plus Fi. Correct? If P min is 0, this becomes Cp over 2. That becomes Cp over 2. This is Pa or Fa. This is Fm. So Fm is equal to Fa plus Fi. That becomes the equation of the line. In other words, the slope of this line is 1. That becomes equal to 1, the slope of the line, in this case. So calculate that. That's your C we calculated at last time, times 2 the maximum force on the bolt, 2AT, 2.12. Then sigma M is that plus Fi over AT. In other words, all we do is just divide this by AT and we get this equation. 2.12 plus 905 divided by AT. Our points to be plotted, 2.12 and 65.9. That's this point here that I've plotted right there. Equation of the load line, Sm equals Sa plus 63.8. Once again, written in terms of these coordinates. And notice once again that the slope is 1 because the minimum value of the load is 0. The slope is 1. The Goodman line, same as before, Sa over 18.6, Sm over 120 equal to 1. And I got 18.6 from those tables. This is a grade 5 bolt. It's fully corrected endurance limit. We substitute for Sm into this equation, solve for Sa, and divide it by sigma A to find the factor of safety, not with Sm and sigma M. Okay? Any questions? I went over far more than I wanted to. Let's take a break, and then I'll continue with another example problem when you come back. Okay, Let's take a look at this problem. It's at the bottom of this page of the handout. It's the same as the problem as before, except that the minimum force is not zero. In problem 834 of the book, assume the pressure inside the vessel changes from P1 to P2, resulting in external bolt forces from 1 to 5 kips per bolt. So minimum load is 1 kip. Bolts are SAE grade 5, tightened to 75% of their proof strength. Check all relevant factors of safety and load factors. So in here, these are the mechanical properties of the bolt, including SE. And AT is here. Our joint constant from before was 0.299. For simplicity, I've just assumed it's 0.2. It's an assumption. You can use 0.299 if you want, just for simplicity, nothing else. Initial preload, 75% of the proof strength, 9.05 kips. F max, CP max plus FI. C, P max, FI, 10.05. F min, 9.25, exactly the same way. Alternating value of the force, F max minus F min over 2, 0.4. Mean value of the force, 9.65. These we've done before a number of times. N for proof, you just put those all into this equation, 3.01. And of course, remember that here you use P max, because if you are going to exceed the proof load, it's going to be with the maximum value of the load, not the minimum. Same thing in here, joint separation. So those are okay. Fatigue, you find the alternating and mean values of the stress. P max minus P min over 2AT, 2.81. Mean values of the stress, the same thing, P max plus P min divided by 2AT plus FI over AT, which gives you 68. So your point is about 2.8 KSI alternating and 68 mean. So 68 is somewhere in here and 2.8 is just above that line. Notice that what changes, in other words, the externally applied load, produces a very, very small variation of stress as compared to the total stress in the material. That's because of the high preload. What gives you the variation of the stress is the externally applied load, not the preload. Because of the high preload, this variation in the externally applied load, which gives you sigma A, the alternating component of stress, is relatively very small. So equation of the load line, we've written that many times. Here's the equation of the strength line, straight from the previous page. And this finally, when we input the values, SM is equal to 63.8 plus 1.49 SA. We substitute for SM in the equation for the Goodman line and solve for SA and come up with the factor of safety. Okay. Any questions? This concludes bolted connections, except for some cases where they actually come up in structures. And the bolts are not under tension like we have here, but under shear, as you see on the screen. So we would like to look at bolts or rivets. You can apply this to either one. You can apply it to either one. If you want to connect two plates together. One way to connect them is via rivets like this. You've got two plates and you put two rivets on it like that. And the loads that are applied to the plate are like this. This you see most often in structures, beams and columns that are made of steel, let's say, and connected together via bolts and rivets. Clearly, when you have these two forces, at the junction here, the rivet is put under shear. There's a shear stress on the rivet or bolt. That shear force causes a shear stress in the bolt. And that's what we would like to find. One thing that happens with a joint such as this is that these two forces, of course, have to be equal because you need to have equilibrium. But they are also a little distance apart from one another. There's a little perpendicular distance between them, meaning that they generate a couple. And that couple tends to turn the joint like this until the two forces are lined up. The analysis of that type of deformation is very complicated, not very easy, and we're not going to do it here. But if that really is something that you should not have in any design, then you can, instead of having this is called the single shear rivet. Instead of having a single shear rivet, you can have a double shear rivet, like that. Still connecting two plates. You put a plate on top, plate on the bottom, bolts. Now the loads are lined up. No bending will occur. And you only have shear forces. And you have shear forces here and here. In other words, the shear force is divided into two. Each half of it is taken by that part of the cross-sectional area of the rivet or bolt here. So we will take a look at single shear, but this is one way to avoid that rotation. Going back to this is shear of bolts. That's how it fails. Another way the joint can fail is by the plate snapping here, failing in tension because of not enough cross-sectional area. Or you could have this type of failure called a bearing failure. This is a compressive failure. This is when the bolt presses against the member and actually crushes the member. Something so you remember this. It will look like this type of failure. I'm going to that side. That didn't work. This, and hold it up like this. This is a bearing failure. It's a compressive failure of either the bolt, rivet, or the plate. So we would like to take a look at these different types of failures and come up with reasonable values for the applied loads. Other types of failure include shear of the plate over here, or tension of the plate like that, opening up of this plate. These three, that one, this one, and that one, these three failures, D, F, and G, can be taken care of if we make sure that the bolts are far enough from the edge of the plate. In other words, if we take this edge off to the right and that one off to the left, we'll have enough cross-sectional area to prevent this failure. If we take this distance between the bolt that used to be here and make that distance larger, then this shear area will be larger and we prevent this type of failure. If we make this distance larger, then we increase the cross-sectional area here, we prevent that type of failure. So all of these can be prevented by situating the bolt away from the edges of the plate. What we would like to take a look at now is this failure and that failure, these two. Just to show you what happens in a bearing failure, things look like this. There's a bolt here and pushes against the plate. If you take a look at the plate, the pressure on the plate, or the stress on the plate, in this case they're both the same, is distributed like this. It's highest in the middle, and it decreases as you get to the edges, and it's of course zero at these ends. If you want that maximum value of the stress, you can find it, but you have to go through an integration process. We usually simplify the matter by saying that we will take an average stress on the bolt, average bearing stress, and just simply divide the load by that cross-sectional area. So that this compressive stress sigma will be equal to the force in the rivet or bolt divided by the thickness of the plate times the diameter of the plate. So this is the diameter, and that's the thickness of the plate. So we compare that with the yield strength of the material with some factor of safety. Insofar as shear forces are concerned, if we only have one or two bolts like that and a shear force, it's not a big deal. Everything is in line. And you divide the load equally between the two and find the shear force and calculate the shear stress. But what if you have something like this? And the force that's applied is applied like that. Now, this joint is not under just an axial load. Here is an axial load. I mean axial in terms of the plate. There's also a bending moment. So what we do is we bring that force down to the centroid of all of these. This is force F, that's force F. With it, we'll bring its moment as well, where this distance is L. And then we analyze it in a way that I will talk about right now. Generally, let's take this situation. Rather than bolts being arranged in a square, let's take this situation. Those are your bolts, A1, A2, A3. Those are areas of the bolts. We find the, so let's say these are the bolts. We find the centroid of the bolted connection, centroid of all bolts. And it relates to their areas. Remember how you find centroids? We have from statics, x bar equals summation of AI xi divided by the summation of AI, right? And the same for y bar rather. Once we find that, once we have found the centroid, then we bring the load down to the centroid. We put it over here, So there's the force now at the centroid, F. And with it has come this moment, M. We say the forces in the bolts or rivets come from two sources. Your book calls this source a primary source, and that one is secondary source. Which is okay, I don't know why, but it's all right. We divide this force equally amongst all rivets. So the primary force F prime is equal to F over N. Force, total force, divided by the number of rivets or bolts. That's the primary. To find the second one, we say, well, when you apply this moment, what can you say about rivets or bolts that are closer to the centroid and those that are farther? Which one takes more load? From the moment, only from the moment, not from the applied force. If I apply a moment to the centroid, bolts are situated at different distances from the centroid. Which one will be under a larger force, takes a larger force? What if I have a bolt right here? How much of the moment force does it take? If I have a bolt and I apply a moment here like this, do you understand what I mean by moment? How much of the moment? Let's make that clear. When you have this moment here, that generates forces in the bolts that look like this, right? Applied, well, let's put it on the other side. Applied like this to this bolt, F1, for example, applied like that to that one, F2. Correct? You understand that? I'm trying to rotate the two plates relative to one another. What if this bolt is at the center? And I apply a moment. Will there be any force in that bolt? No, there won't be any force in that bolt. The farther apart the bolt is from the centroid, the higher the value of the secondary force. Because the farther it is, by rotating this, if it is up here, you rotate it through that length. If it is down here, you only rotate it through that length. So the farther it is, the more load it will take. So we say that the secondary load is like this. F double prime I, well, let's say 1 divided by R1 equals F double prime 2 divided by R2, like that. And the sum of the moments generated by all of these forces about the centroid must equal to the applied moment. So M is equal to summation of Ri Fi double prime. We solve these two equations together one by one. One's like this, one's like this, with 2, 3, and so on. And we get the secondary load in the bolt equal to Fi double prime equals MRI divided by the summation of Ri squared. I'll do an example problem to show you how this works. Any questions? Okay, please put everything away. We'll have a quiz.